Right. So yeah, today I will go more into like not really the technical details, because this was a bit more last year kind of thought, like more about like the general framework, the performance, and what we've been doing with it. So yeah, if you can leave a star on the GitHub repo, it helps a lot for packaging. Just saying. Anyway, how it all started is quite simple. I was due to do a PhD in theoretical physics, mostly to look at early planet formation, dust gas instabilities, and whatnot. I've been coding on GPU for quite some time already, and started a side project of mine, which turned out to be my PhD. Anyway, fast forward many years, we now have the code, and I work with a superb man right there. On mostly like on dust aspects, trying to basically connect more and more on the physical aspect of dust with observations as much as possible. And can I get this thing off? I hate the interface so much. Now it's better. Anyway, so last year I had the opportunity to present it at the Phantom Workshop in Australia, but my talk was not really in person for reasons. Anyway, so you may ask, why not using Phantom? In general, like why do we need a new code? For some reasons, mostly because sometimes we need a lot of resolution. As in, we can look at a few examples. One of which can be global instabilities, for which you will need to resolve at least 100 particles per scale life in a disk, which turn out to be in the neighborhood of 1 to 10 billion SPH particles for a full disk. Yona here will be more interested in something like the Bardeen-Peterson effect, same as Beck, which will estimate to become sufficiently resolved close to the billion SPH particle barrier too. Circumstellar accretion could be one of them if you want to resolve also the density in the innermost cavity, where the density contrast is pretty low. You will need a ton of particles. Or lastly, if you want to add an envelope to an existing disk while having also a low viscosity, you will need also a ton of particles. In general, thanks to Cristiano, I have this estimation. With a billion particles, you are in the neighborhood of 10 to the minus 3, 10 to the minus 4, if we are being conservative on the alpha in a disk. So if we go even beyond, we can, in principle, resolve stuff like, for example, the Rossby wave instability that is quite sensible on the value of alpha. Anyway, so you may ask, can we use Phantom on GPU? Well, you have the Phantom SPH code. On the other side, you have an exascale supercomputer, which does 1 exaflop, which means a billion of a billion floating point operation per second, which is a tremendous amount of power. But sadly, we cannot use Phantom on such a beast because it's a CPU-only code. It doesn't really scale on the MPI side, which means that overall you have a soft limit around 10 to 100 million SPH particles for the larger simulations. On the other side, so quite early in my PhD, we saw that we cannot really port Phantom onto GPUs for many reasons, the KD tree, domain decomposition, the fact that Phantom is using a single loop approach. So we just restarted and developed Shamrock. Anyway, on the other side, if you look at supercomputers, this is the first entry on the top 500. So this is the 500 most powerful supercomputer in the world. I'm only showing the first 5. And you may see that on all of them, you have GPUs, actually. Even worse, GPUs from all the different vendors, which is annoying, to say the least. On the other side, Andrew's talked a bit about this yesterday, but basically, supercomputers are moving toward GPUs, and there are people waiting at the entrance. If someone can open them. Anyway, so in general, we are moving also toward GPUs for many reasons, density, efficiency, AI, and so on. Such a thing could also happen in the future with a neural processing engine, typically. So basically a GPU for matrices. But yeah, this is the trend for now, and we have to deal with it. Anyway, In order to support all of the different vendors that are on those clusters, we are using SYCL, which is a programming standard built on top of C++17 that can directly compile your code to CUDA, HIP, or OpenMP, which means that you will have close to native performance and actually that your code will be basically undistinguishable from CUDA from the point of view of NVIDIA tools. I mean that you can use, for example, NVIDIA profiling tools, AMD profiling tools, or whatever you prefer. Also, we support CPUs because SYCL can be compiled also to CPU using an OpenMP backend. Anyway, so the goal on our side is to go toward exascale. How do we do that? Basically, the take of Shamrock is to do absolutely everything on the GPU, even stuff that wouldn't be efficient, just because we don't want to get out of the GPU to avoid like wasting time. So within each of the GPUs, we are using SYCL to do the computation, and we are communicating between the GPUs using MPI in a direct fashion, as in each GPU in those supercomputers have a network cards that are directly attached on the GPU. It's a weird thing, but that's the way it is. And with MPI, you can actually communicate directly from a GPU to another GPU in the machine. Anyway, if you want more details, you can look the first paper that is, published finally after years of battle. The smaller version that is in the proceeding of the SYCL conference, or my talk at SYCL this year, where I go more into like the algorithmics and the technical details of the code. Anyway, so two-slide summary about what is Shamrock will be that basically you have three methods in astrophysics: finite element, finite volumes, and SPH, and all of which can be summarized in the same aspect, as in you have an interaction criterion that tells you whether two objects are neighbors or not in your simulation, and on the other side, a numerical scheme that will say that each element in your simulation will be updated as a function of their neighbors. Of course, this means that basically cells or like grid cells are just particles that don't move, and that's one of the way we deal with that. So in Shamrock, we are trying to have a general framework where you can supply such a criterion and such a scheme and hopefully get a numerical method with exascale scalability. This means that also, if you are optimizing the SPH, you are also optimizing the IMARC scheme that is in the code and inversely. Lastly, if you have any generic modules, for example, equation of states, it's the first one that can come to mind, they are coded once for all the schemes. Of course, reality is a bit more nuanced, but that's what we are trying to aim towards. Anyway, so on the SPH side, you may know this test. This is the set-off blast wave. Here you can see two sets of simulation. One is a phantom simulation, the other one is a Shamrock simulation, both of which were restarted on the same phantom dump, and you get basically exactly the same result down to floating point precision. So we reproduce phantom solver. This was something that was very important to us, as we aim basically to have a GPU accelerated version of Phantom initially, at least on this, and we have to at least achieve parity on the solver and get the same precision on the same test. This makes us more confident when we use the code overall. Anyway, but we don't have only SPH. We have also adaptive mesh refinement, as in the Ramses kind of solver. It's actually the core of the Ramses solver without individual time stepping and without MHD for now. We also have implemented the Zeus scheme in the code, both of which here are not production ready yet. SPH is really the most mature solver in the code right now. Anyway, maybe you want to go a bit more into performance. So always we measure performance in number of particles treated per second. So you take a simulation, you take the number of particles, divide by the time per iteration, you get the performance. First off, we can start on a good bit, EPIC 7742 CPU. It's a 64-core CPU. For Phantom, it's probably like one of the best performing one. Maybe now there are latest like EPIC CPU that can do slightly better than this, but it was basically at the time the best CPU for Phantom. So we run Phantom on this same set of blast wave and vary the resolution. You will see that whatever the resolution, you get about 2 million particles treated per second with Phantom. Now, if we take Shamrock, compile it on CPU also, and run it on the CPU, you will see that we get basically very similar performance, if not like slightly better by few%, but whatever. Now, Shamrock can run it on GPU. Here, A100 GPU, you see that you move up by quite a lot, actually, by a factor 6 in
progress.
All right. It's good. So now we can go on multiple GPUs. Many supercomputers, including the LUMI supercomputer. Anyway, but this isn't exascale yet. Now we want to go higher, larger. And to do that, it's so simple, just add a ton of GPU, a lot more of them. And if you go back to the 500 most powerful supercomputers in the world, you have many interesting ones. Not the first one, because it was public for 2 weeks before it was closed by the military, but whatever. But we have access to that one, which is exascale. It has like 100,000 GPUs. Getting GPU time also is really easy on that one. Basically, you just ask, and provided that you want to do like interesting physics on it, you will get time. There is not much pressure there. Anyway, this is the result. So the orange curve here is the test we did on Adastra. We went quite higher. We went on 10,000 GPUs with some nice numbers again. Close to 500 billion SPH particles at a rate of 10 to the 11 particles treated per second, which is about 4 seconds per iteration on that beast of a simulation. And that is on 12,000 GPUs this time. And here you can see the log. First off, that we are using 300 terabytes of memory at a given instance. But most importantly, that every one of those tiles, and there is a 12,000 line in that table, are all running 36 million SPH particles. So you have a lot of them. Just for reference, again, this is 50,000 times speed up compared to the baseline test we have with Phantom. Anyway, now we can look at the parallel efficiency, and on that part of the cluster, so 10,000 GPU, it's about 80% parallel efficiency. We want to go even higher because exascale, it's not there yet. This is only a tenth of the supercomputer. We still can get a factor 10 out of it. And we are trained quite hard, but MPI is very, very buggy beside that, like the actual implementation, not our use of the implementation, sadly. So we have to debug MPI itself. It's great. Anyway, the next step for us is exascale on this. Maybe you are interested in actually seeing simulations now. So for that, there is quite a good test. So last year, you maybe saw the Santa Barbara code comparison paper that compare many codes on the problem of circumbinary disks. Here you can see multiple simulations. The first one using Shamrock at 10 million SPH particles, where you have gas that starts to fall in the cavity. But as you can see, you get basically nothing. The resolution is way too low in the cavity because the contrast is 1 to 1,000 about. So you don't resolve anything. At 100 million SPH particle, it's a bit better. Yeah, you're starting to get some circumstellar disks, but as you can see, one just goes away because, again, not enough resolution in that disk. So what we did is that we used the leftovers time we had on Astra, and over the course of 3 days, run this simulation. So this time at 1 billion SPH particles. As you can see, the features on the edge are way sharper, and we actually get circumstellar disks with even tidal features in them. I'm wrapping up.
You don't show them?
Hmm?
If you don't show them, I'm not doing this.
I haven't seen. You did? Okay, sorry. I haven't seen it. Okay, whatever. It's finished anyway. So you get a much more precise accretion rate because you are resolving the circumstellar disk, which act as an accretion buffer, blah blah blah, and even you have about 100 particles per scale life. This means that it's enough to resolve actual instabilities in the disk. Where do we go from here? From there, you can see Guillaume's talk for more of like a perspective and background on all of this, and Jonas talk for disk simulation. And well, we have many things in the solver. We are planning to implement many more. And